Here we go. In this video, we're gonna learn about Hamiltonian path and circuit. So we have this question: Hamiltonian path. What is a Hamiltonian path? It is a path that visit each vertex exactly once. And how it is different from Eulerian path? So in Eulerian path, we visit every edge exactly once. So in Eulerian, we visit edge, and in this case, we visit every vertex. So how it will make a difference? So let me show you an example. So let's suppose we have this test case. So first we visit this, then we visit this, then we visit this, then we visit this, but we cannot visit the same visited vertex again. Visited vertex again. So this is not a Hamiltonian path, but this is a Hamiltonian, this is a Eulerian path. How? First we visit this edge, then 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 we visit this edge. This is Eulerian path, but not Hamiltonian path. So that's how. So that's the difference between Hamiltonian and Eulerian. So let's come back to the question. We have this. So we have given edges 1, 1 to 2, then 2 to 3. So let's create the graph. We have a edge from 1 to 2, then 2 to 2 to 3, 3 to 4, 2 to 3, 3 to 4, then 2 to 4. So is this a Hamiltonian path? First we visit this, then we visit this, then we visit this, then we visit this, and we have visited all the vertices. So this is a Hamiltonian path. So in this case we have to return 1. Then we have another test case: 1 to 2, 2 to 3, 1 to 2, 2 to 3, then 3 to 4. So this is not a Hamiltonian path, neither a Eulerian path. So we have to solve this question. So let's build the approach. So let me take a test case. Let me take a test case. So suppose we have this 1 to 2, then 3 here, then 4, then 5 here. So can we start from this? If we visit this, then we come here, then we come here. So starting from this particular vertex is a bad idea. So we have to check for each and every vertex. So I hope you got my point. We have to check for each and every vertex. Can we start from this? If we start from this particular vertex, we visit this vertex, then 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 we visit this vertex. So there are multiple ways. First way is this, and second way will be this, second way will be uh, this, and third way will be this. So there are multiple ways, and this is a Eulerian, this is a Hamiltonian path for sure. So we have to check for Eulerian path. So we have discussed about Eulerian path. So in this case, so for Hamiltonian path, we have to visit each and every vertex. So each and every vertex, first we visit this, then we come here, then we come here. But what about Hamiltonian circuit? So for Hamiltonian circuit, the first and the last, vertices should be neighbor vertices. So that's about the Hamiltonian path and circuit. So I hope you got my point. This is Hamiltonian path, but this is not a Hamiltonian circuit. So let me show you another test case. So first we visit this, then we visit this, then we visit this, then we visit this. So this is a Hamiltonian path and this is a Hamiltonian circuit, both. And this is also Eulerian path and Eulerian circuit. So in this video we're gonna focus only on Hamiltonian. So we have to check, is this a Hamiltonian path or not? So first of all, we will start from each and every vertex. Before that we have given edges, so our first step is to convert edges into adjacency list. After that, what we will do, try uh, we will try to start from every vertex, and we will try to visit as many vertices as possible. And if we have visited all the vertices, then we are sure that this is a valid Hamiltonian path. The question is only for Hamiltonian path, and you can further modify it to check if this is a Hamiltonian circuit or not. I will discuss about it later. So now we will try to visit, and let's suppose we have taken uh, let's suppose this is not there. So what we'll do, we start from here, then we go to this, then this is visited vertex, so we will not come back here. We try to visit unvisited vertex, so then we come here, then its neighbor is visited, its neighbor is visited, so then we try to find unvisited neighbor, so we go here. Then for this particular vertex, so there may be a chance, let's suppose we have this, so there may be a chance that we have taken this, then this, so we have taken this route, but suppose this route is not valid, this route is not valid, this route is valid. Suppose this route is valid, so we have considered, we have visited this, 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 then we have visited this vertex, then we are doing backtracking, so we will remove this from our visited set, or you can say our array, visited array. So then we try to go with a different route. So if this route is valid, and we using this route we have visited all the vertex, then we can say this is a valid Hamiltonian path. So let's code this. What we have, first we have edges, so we have to build urgency list. So I have built our initially in empty list. After that we have to add from u to v and v to u, this is a undirected. After that we have to iterate and try to find from each and every given vertex, and this is a one base indexing, so we will start from 1. We will start from 1. We have set this, will check if if any particular node in our DFS function is visited or not. So if this is not visited, you can directly you can directly call the DFS function. In the DFS function, here I am calling my DFS function. In the DFS function, first I am adding the particular vertex, and if I have visited all the vertices, this is my base case, then we just need to return true. For Hamiltonian path, how we can modify, we have at last node, so we just need to check we are at the ending node, so we just need to check if there is a direct edge present from last node to starting node. Like I have shown you a square, so that square is a valid Hamiltonian circuit, sorry. So for that case we need to just check if there is a valid edge present. We need to maintain the original source in the argument, so we in the argument we have a separate source, so we will not change the source. Then we need to we need to visit the neighbor nodes, we need to visit the unvisited neighbor nodes. So neighbor nodes using the source, if the neighbor node is unvisited, we are just calling our DFS function, and if that route is valid, we just need to return true. If this particular route is not valid, we need to do backtracking and remove this particular node from our visited set. Then if none of the path is valid, just return false. And here let's continue from here. If we have found if we have found any valid path, just return true. After that, just return false. So I have discussed about Hamiltonian path and Hamiltonian circuit. Let's give it a try. And now let's talk about time and space complexity. So here we have DFS function, and in the DFS function, we are calling it for every single node. So we are calling it for n nodes, and in that we are traversing n minus 1 nodes and then n minus 2 nodes for every single time we are decreasing a value. So the total time complexity is n factorial, and space complexity we have given edges. So we are creating a lift, a recency lift. So the space complexity is n plus m. We have solved this question. Code is given in the description box. And if you guys have any doubt between Illyrian or Hamiltonian path or circle, path or circuit, so feel free to drop a comment. Then thank you all for watching.